Okay, starting from our previous lecture, we talked about the secular equation, this sort of matrix method for solving the Schrodinger equation in quantum mechanics. And now we're going to apply that to another important theory in quantum mechanics, which is perturbation theory. And this is a very powerful general way of solving Schrodinger equation for a lot of complicated systems, such as systems that involve many interacting particles, multiple electrons, multiple nuclei, and so on. And for these kinds of systems, as we know, um, in both Newtonian mechanics and quantum mechanics, in other words, Newtonian or classical mechanics, and in quantum mechanics, there's no simple closed form analytical solutions to these systems. And so we're left with either using kind of brute force, computer based computational methods, or coming up with various analytical approximation methods, which can serve a couple of purposes. One of those purposes is to, of course, help us to design the brute force computer based systems for solving the Schrodinger equation for many bodies or other complicated systems. And another reason to have these is that we can perhaps look at some special cases where we can have analytical closed form solutions to an approximation of the problem. It's not going to be necessarily as accurate as the complete brute force approach, but perhaps it will allow us to make certain observations, develop and test hypotheses, and so on, because because the because of the power of symbolic algebra and calculus, in that there's clear relationships between the various variables and parameters in the system. So we don't want to sacrifice that. We want to keep that power of analytical tools, but we also want to have tools that can help us to solve more difficult problems. Um, anyway, so perturbation theory, yeah, it's the starting point for a lot of widely used physical and chemical models. As we'll see, the Huckel model. It also can be tied to MO-LCAO theory, and perturbation methods are used, implemented in a computer in an iterative fashion to get very good quantum chemical calculations for predictions of total energies and bond energies and structures and so on and other properties of molecules. So perturbation theory, quite useful. And it also, there's something called time-dependent perturbation theory, which we probably won't have a chance to get into, but that describes the interaction of, say, molecules undergoing some kind of chemical reaction, or molecules interacting with light, and so on, and the sort of spectroscopic selection rules. And so there's, and how lasers work, and a whole lot of interesting stuff. So yeah, perturbation theory really opens up a lot of vistas into molecular systems, and does it with amazing accuracy and amazing descriptive and explanatory power. All right, so without any further ado, let's talk about the basic starting point of perturbation theory, which is this describing the Hamiltonian here, H, as we just sort of separate it up into two terms or two collections of terms. There's H aught, the sort of zero order Hamiltonian, plus V. So H aught typically describes a simpler system, something like an H atom or a particle in a box or a rigid rotor, or a quantum mechanical harmonic oscillator, or something like that, where we have simple expressions or relatively simple expressions for the various wave functions for that simpler system. And so there's this simpler part of the Hamiltonian, and then there's this perturbation potential V, or V pert sometimes, or VP. And that's our perturbation theory, and it's essentially the difference between our H aught and our full Hamiltonian H. And so it's going to have, the terms that we need to include multiple particle or multi-body interactions in our system. Things like electron-electron repulsion, um, things like interactions of an electron with two or more nuclei, so the presence of that extra nucleus can be treated as a perturbation. Also, of course, if we take our molecule and apply an external electric field or magnetic field or something, that can be treated as a perturbation, and so on. So that's where the complicated part is in this V. And so by splitting this up, then we also are assuming that our H aught, our zero order Hamiltonian, has a set of wave function solutions psi I aught, right? And an associated set of energy levels EI aught. And we're going to use those. So this psi I zero, or this zero order wave function, that's going to be our basis functions for the secular equation. So if those are our, as I said, those are the basis functions that we use, then the individual Hamiltonian matrix elements for the full Hamiltonian here are going to be this integral over all state of psi I aught star H psi j aught d tau, integrating over all space. Of course, then we can replace this full Hamiltonian with our representation as H aught plus V. And then the H aught, we can see, acts on the wave function to the right here. Right, so this one's going to act on that wave function to the right. And so that's going to give us an EJ. So if we distribute and split up the integrals, we get something that looks like this. Hij is equal to Ej aught times this integral of psi aught I star psi aught j d tau, and then plus this other integral that just involves the perturbation potential, and it's sandwiched between the zero order wave functions psi I aught and psi j aught. And we can represent the result of that integral as simply Vij. So presumably, whatever that potential is, we can evaluate it at every point in space and multiply it by the psi I aught, psi j aught, again at each point in space, integrate, and we should get a number. We'll call that number Vij, so represent the outcome or the result of that integral there. Now, this other first part of the Hij, that's actually even simpler, because these psi I aught and psi j aught are different states of the zero order Hamiltonian, therefore they must be orthogonal. And therefore that integral simplifies. If I equals j, then that integral equals 1, right, because they're an orthonormal set. And if I is not equal to j, then we get 0. And that's the Kronecker delta. Kronecker delta is delta ij, where if I equals j, we get 1, or when I is not equal to j, we get 0. And so then our Hamiltonian reduces to this expression, this very simple algebraic expression, Hij equals Ej aught delta ij plus Vij. And then we can think about it in terms of the diagonal and off-diagonal elements of our Hamiltonian matrix. Along the diagonal, we're going to get EI ought and VII. And then off the diagonal, because again of that Kronecker delta, that's going to zero out the E ought J terms, and so we're just going to get VIJ. So that gives us our Hamiltonian matrix. Then we just have to solve the secular equation to find energy levels, and these, and also we can get these linear coefficients to back out what the wave function should look like. Okay, in terms of these linear coefficients, in terms of these, this superposition principle. Okay, so that's essentially perturbation theory. At this point, it's a matrix equation, and you have to solve it. Now, we could stop there and say, well, now it's just we've turned it into a computer problem. However, there are some simple cases that we can solve analytically, and let's look at those. So those cases will be typically involve very few states and may involve some restrictions regarding energy levels and the values of certain integrals. So let's look at one very important case, which is, well, let's say we have a system and there are some multi-body effects, but they're weak, right? They're a weak type perturbation, and maybe we have a very weak external electric field, and we want to see what happens to our system if we just apply a little tiny bit of an electric field to it. How's it going to react, right? And that would be, say, a way to look at polarizability of a system, for instance. So here we will start with our zero order or our unperturbed system, our psi oughts and our E oughts for our zero order Hamiltonian. And so we've got a two-state system. So we've got psi A ought, psi B ought, and then they're going to have corresponding energy levels. We'll call them epsilon A ought and epsilon B ought. We'll use little epsilons because those aren't the true energies of the system, and so we want to give them a funny symbol. So we think of them as they're like energy, but they're not the energy of our system. Okay, so and then again, our unperturbed system, H ought psi A ought equals E A ought psi A ought, etc. And so then we can construct our Hamiltonian matrix, and it looks like this. The H11 term is going to give us EA ought plus VAA, and then our H22 or HBB term gives us E ought B plus VBB, and then of course we have these off-diagonal terms, and those are going to be VAB and VBA. But since we think of the perturbation as being sort of a force or a potential, then VAB is equal to VBA, since it's just going to involve some integration over ordinary functions, and it's not going to depend on the order of those functions. So we'll just use VAB, and that simplifies things a little bit. Also, another important thing about VAB is that we need to be careful here. We're defining this as a weak perturbation. So I was a little bit vague about that previously, but here's a good place. We have enough sort of pieces of the puzzle here that we can state what we mean by weak perturbation. And weak perturbation means this integral, VAB, it's going to have units of energy, and the absolute value of that should be much less than the separation between the energy levels of the unperturbed states. So this would correspond to a weak perturbation, right? That the average of this perturbation potential over these states is going to be much less than the actual difference in energy between those states. So that's how we're defining weak perturbation, and that's a useful Uh, it may sound a little strange to define it that way, but it holds up. Most actual weak perturbations are going to follow this, even if it's not clear that that's the case on first examination. Okay, so now let's uh, consider how to solve this. And again, the VAB is just that integral, this kind of cross term between the zero order wave function for state A and for state B of the zero order Hamiltonian, multiplying that by the potential, the perturbation potential, and integrating over all space. This is going to give rise to a secular determinant that looks like this. And this will give you, you can multiply this out, set that determinant equal to 0. And it's a little bit long. You can see it's in the PDF version of the notes. Getting there's an awful lot of variables to keep track of in there, and so it's kind of difficult to generalize from that result. So let's look at a specific case where VAA equals VBB equals 0. And this might seem like a rather strange case to consider, or rather strange sort of requirement to impose sort of after the fact, after we've started the problem. However, it's fairly common in that if our perturbation potential has, say, an odd inversion symmetry, then we can that integral VAA is going to be 0. Another way to look at that is a lot of times you can just take the result of VAA and VBB and sort of plop them into E aught A and E aught B. So then they just sort of disappear. We've just sort of hid them in a different term by moving some terms around in our equations, and we can do that, right? Anyway, so this is an important, not completely general, but common enough case, and it really allows us to simplify the result. If we do that, and it turns out it's still, you end up with a quadratic equation. It's still a little bit messy, but we get a result that is to a pretty good approximation. Again, assuming that the VAB, the energy associated with that, is much less than E aught B minus E aught A. Then we get that our energy for the lower energy state it's pushed down a little bit in energy. It's approximately E aught A minus this VAB squared divided by the difference in the initial energy levels of the unperturbed Hamiltonian. And then our higher energy state, it gets pushed up in energy a little bit. It ends up being E aught B plus VAB squared divided by the difference in the initial or unperturbed energy levels. And let's see what else to say about this. And because of the initial assumption, this second term, this VAB term, is always going to be much less than your initial energy. So this is showing that the effect of the perturbation is it's twofold. One is it pushes the states a little bit further apart, but it's not going to push them apart much, because it's a weak perturbation. It's also going to mix the wave functions together a little bit. And we can sort of generalize what's going on in this perturbation in that we can maybe perhaps start with a weak perturbation and apply it multiple times to our system. And then that will add up to a larger perturbation. And if we do that, we're going to see that these states will mix together. And so if we look at the, and it'll push the wave functions a little bit further apart each time there's an interaction or perturbation. Similarly, the wave functions are only slightly perturbed. Our perturbed wave function is almost equal to the same wave function that we started with just this tiny term. Again, we know that VAB, we've defined it as being much less than E naught B minus E naught A. And so, we're going to have maybe a few percent of psi naught B in there. So like if this were a two-state system, like maybe the first two states of a harmonic oscillator or the first two states of a particle in a box, where you have sine or something like that, then there's going to be a slight change in the shape of the wave function, but it will still be recognizable as having a lot of character similar to the original particle in a box wave function, just maybe a little bit tilted or something like that. So our wave functions are slightly mixed. Now let's look at the other limiting case. Let's look at the limiting case of a very strong perturbation, or equivalently, essentially our two states start off very close in energy, or at least they're very close in energy relative to the strength of the perturbation potential. So you can see that this example 2, this degenerate case, is equivalent to the strong perturbation limit. And then we'll talk a little bit about the intermediate cases after we finish with this case. Okay, it's degenerate, so we're only going to have one E naught, right? So we're not going to have E naught A and E naught B, it's just one E naught. We'll plug that into our Hamiltonian. We get E naught plus VAA at the HAA term. And then HBB is going to be E naught plus VBB. And then, of course, we have our VABs, our off-diagonal terms. And again, as above, for similar reasons, we're going to simplify by assuming that VAA equals VBB equals 0. And then we end up with a very simple cyclic determinant, and it really just boils down to E equals epsilon naught plus or minus VAB. Very simple. So our perturbation essentially removes the degeneracy. So we start off with two states at the same energy, and now they're going to be split by 2 times the absolute value of VAB, where VAB is that integral that we talked about previously. Also, this is going to completely mix the wave functions. In other words, we're going to get a 50-50 superposition so that we have two wave functions, this kind of plus state and this sort of minus state, very much like what we saw with H2 plus. Right, the form looks the same. And so it's, 1 over square root of 2 times psi A naught plus or minus psi B naught. And which of these corresponds, which of these kind of combined or perturbed wave functions corresponds to the lower energy state really depends on the symmetry of the wave functions and the sign of VAB and that sort of thing. And you just kind of have to look at your system or consider the specifics of it in order to figure out what's going on and then maybe test it. But yeah, we've completely mixed the wave functions. So now we've dealt with the two limiting cases in fairly short order. The very weak perturbation case, the very strong perturbation case. In the intermediate case, we can either treat that as multiple weak perturbations or just use matrix methods and solve the resulting quadratic equation. There are some conclusions that we can make about all of this. So states that are nearby in energy, even with a tiny perturbation, it's going to completely mix them up together, right? And that also implies that only states that are nearby in energy are going to interact or perturb one another to an appreciable degree. Okay, and we already kind of assumed this in our MOLCAO, in that we typically we made the MOs out of atomic orbitals that were close by in energy. So we didn't have, say, if we were looking at N2, we didn't bother looking at the combination of, say, a 1s orbital on one of the nitrogens with the 2s orbital on one of the other nitrogens. They're just too far apart in energy. They're not spatially overlapping, and that's another important issue in this kind of perturbative approach. And if they're not spatially overlapping, then that VAB is not going to be very big. It's going to be 0 in most places, except where they overlap. So yeah, again, we sort of already saw some aspects of this in the MO-LCAO, and it allows us it justifies this rule that we sort of previously implicitly assumed. Or assumed without justification, which sometimes we kind of have to. There's a lot of stuff to cover, and hopefully you'll circle back and figure out what the justification is, which we've done. So we've looked at the two-state system, two different limiting cases, and that may seem like it's not applicable to many systems, but first of all, in the in-between cases, those aren't really that much more complicated. Again, pretty easy for a calculator to deal with it, even just a hand calculator. If we're dealing with 3 or more states, you might say, well, this is 2 states. How many systems have just 2 states? Well, we can often approximate a 3 or 5 or 50 state system, sort of one pair of states at a time. And that's a pretty good approximation, and so we can apply this to those more complicated systems, sort of one pair at a time, and that's a common technique in physics and so on. This sort of pairwise interaction approximation, and again, if we want to look at 3, 5, 50 states and make a big matrix, we can hand that off to a computer and have it give us results relatively quickly, assuming that we can evaluate all the integrals, and that's probably where a lot of the time gets spent, not so much in the linear algebra part. But those integrals are fairly straightforward. Let me just end by summarizing what we found here using a graph. And so if we plot along the x-axis E naught b minus EA, so we start the origin there is kind of on the left, and then we sketch a line for E naught a, that's going to be going down as the splitting goes up. E naught b, it's going to be going up as the splitting goes up, right? So that's this one. And then we've got our E naught a line there. At the origin at 0 here, we've got no splitting between E naught b and E naught a. There, our final state energy, the difference between the energy levels of the 2 states is 2 times VAB, shown here on the left here by this arrow right here. And then as we start to increase the splitting between those E naught A and E naught B, we see that the difference between the energy levels shown here in the dotted line and the unperturbed energy levels, the difference between those gets smaller and smaller asymptotically as the splitting between E naught B and E naught A gets larger and larger. So that's a nice sort of summary graph kind of showing you what you would get if you plugged in the full sort of quadratic equation for this. We still assumed that VAA and VBB are 0, but that doesn't really change the overall picture very much. All right, so that's about all I have to say about perturbation theory. We ran through a couple of cases. We've talked about the intermediate cases and how to handle larger systems with more basis functions. Next, we will see how to apply this perturbation theory approach to the Huckel model for extended pi conjugated systems and other systems with similar aspects.